Sorry about that. All right. Welcome to class, everybody. Hope you're all doing well. Let's see, a couple things. Play there, sorry. Where'd you go? Apologies. There's a link to the attendance form. Please go fill it out. I am imagining people would like to talk about limits today. Is that true? You guys want to talk about limits? Cool, I see some yes. You can also use the yes, no's on the participants thing if you want. Yes, okay. You can click yes, oh, interesting. How do I turn off my yes? Anyway, cover number 8 on the homework. Sure, let me pull it up 1 second. Where are you? That's a lot of stuff. I need a new window. Not a new tab, a new window. I'm assuming this is Sanders' homework. Certainly, we can definitely look at number 8. One moment. Sanders homework. That's in his files, right? Yeah, homework. Yep, homework 1. Number 8. Sure. So I will say the hard thing about questions like this in general is they definitely take some practice, right? It can be challenging to have an idea of what the what's what I'm looking for. Sorry, let me look at my screen. I'm putting up something. What the sequence they're looking for actually is. Typically, I would say it boils down to there's kind of 3 different things that can happen. Oh, sure. Here's the attendance link. You can hear him, hear me. You can't hear me. Let me check. Let me make sure my microphone's on. Speaker. Everyone can hear me, right? We're good to go. Like volume's good. Okay, Alejandra, I hope you can hear me all right. So number 8, yeah. So as far as sequences go, figuring out the what's the word I'm looking for? Figuring out the pattern for it can be challenging. So I want to do exactly this one. I'm going to make it a tiny bit different, if that's okay, just so I'm not exactly answering your homework, but it's going to be pretty similar. So I see this. I'm going to make it, sure. Yeah, why not? Yeah. -1/4, positive 8/9, -27/14, positive 64/19, and what's -125/24. Let's say those were the terms of our sequence. Let me flip my screen. Sorry, I can't look at my screen if it's all backwards because my numbers are like, oh, it looks wrong. Let's see, video settings, mirror. Okay, great. Cool, now it looks normal. All right, so if we're looking at this, so I see something right off the bat. Well, a couple things, but let's just kind of go piece by piece. It's alternating, so we know we need to have a -1 to something. If we're starting with n equal to 1, so I know that I need a -1 to the n, right? Because if I'm starting at n equal to 1, then if n is 1, I get -1 to the 1, which is -1. And we're starting with a negative term here. If it was positive, negative, then we want a -1 to the n plus 1, so that we can start with a positive instead of a negative. So then we have the numerator and the denominator. I think the denominator is really easy to tell here because it's just increasing by 5 each time, right? The denominator is 4, 9, 14, 19, 24. And that's just adding 5 each time. So if you're adding the same number each time, you know that means you have whatever you're adding times n. So I need to have 5n. Now that's not quite exactly what I need, but it's close. Right? Because if n is 1, I'm going to get 5. If n is 2, I'm going to get 10. And if n is 3, I'm going to get 15. But I wanted 4, 9, and 14. So to get those numbers, I have to subtract 1. Or I just look at the first term, realize that, oh, n is 1, I get 5, but I want 4, so I subtract 1 to get 4. And then whatever n is, right, I'll get this. N is 1, I get 4, n is 2, I get 9, n is 3, I get 14. Yeah. That's my denominator. And now the numerator, I will say, might not be a pattern you're super familiar with, but is really obvious to me because I know these numbers really well. 1, 8, 27, 64, 125. Those are all cubic powers. 1 is 1 cubed, 8 is 2 cubed, 27 is 3 cubed, 64 is 4 cubed, 125 is 5 cubed. So I'm seeing I have n to the third power, where n is 1, 2, 3, 4, 7. And that would be what the formula, or the, what's he used the word here? The explicit formula for the sequence. So this is what my formula would be. The one for the homework is a little bit different because the denominator is something different, but the numerator is the same. So it's something to the third. So if you see something like that, where it's 1, 8, 27, 64, 125, that means a cubic power. Just to go a little more in depth, if you saw this but you didn't see it, you could try using the idea that we talked about before, that the difference of the difference of the difference is constant when it's a cubic power, so 3 difference levels. If it's a first power like the bottom, it's 1 difference level, they're all constant. If it's a square, which we don't have an example, it's 2 difference levels is a constant. And if it's a cubic, 3 difference levels should be constant. So if I look at the difference levels here, and this is kind of hard, but if I do this, 1, 8, 27, 64, 125. The difference between 1 and 8 is 7. 8 and 27 is 19. 27 and 64 is 37. 64 to 125 is 61. And then the differences of those is 12, 18, 24. And then finally, the difference of the difference of the difference is 6, 6, 6, 6. So if you did that, you'd see, oh, if you go 3 levels down, the differences are constant, which means it's something to the third power. I'm sure they don't talk about this in your class, but it is something I have noticed over the years. So that's one way you can kind of try to attack it. But I think his intention with this problem was really to be like, oh yeah, you should be able to recognize that's 1 cube, that's 2 cube, that's 3 cube, that's 4 cube, that's 5 cube, and so on and so on. All right. We can definitely look at number 9. So we did talk about number 9 a couple times already. Really, it's just, so I'll do the first couple, but really for number 9, it's just going to be, you got to just keep plugging it in. So here's how number 9 would start. A1 would be 1. A2 would be 2. And then the next term, A sub n plus 1 is how he's writing it, is equal to 2 times A sub n, right? Sorry, I'm looking at the wrong thing here. No, sorry, A sub n minus 2 times A sub n minus 1. So if I set n equal to 2, I'm going to find A sub 2 plus 1 is 3, equal to A sub 2 minus 2 times A sub 2 minus 1 is A sub 1. So A sub 3 is going to be the previous term minus 2 times the previous term, which is going to be 0. And then to find A sub 4, I'm going to set n equal to 3, because I'm finding A sub n plus 1. So if n is 3, I get A sub 4. So A sub 4 is going to be the previous term, A sub 3, minus 2 times the previous term, A sub 2. So A sub 4 is going to be A sub 3, which is 0, minus 2 times the previous term, which is A sub 2, which is 2. So you get negative 4. And you're just going to keep doing this, right? You're going to say, okay, for n equals 4, to get a sub 5, it's going to be the previous term, which was negative 4, minus 2 times the previous term, which was 0. And then a sub 6 is going to be the previous term, which was a sub 5, minus 2 times the previous term, which was a sub 4, which ends up being negative 4 plus 8, which is 4. And then you're just going to keep going. You'll have a few more to go. I feel like I shouldn't finish the problem for you guys, but that's kind of the idea there, right? Is you just keep using the previous two terms in this formula, where it's the previous term minus twice the previous term, and you just keep doing that to get whatever the last term is. If you want, you can also post a discussion in, what's it called? Canvas, and some of your classmates could comment on it, but I feel like I shouldn't exactly answer the homework question. At least not, well, yeah. Anyway, also, just so everyone gets it, please go fill out the attendance thing. All right. And then someone said something similar to problem 6. Sure, so I will point out for problem 6, I did post a couple videos on YouTube. You can look at those as well. So we could definitely totally do a problem with some of that, because it is something that comes up a bit. So the thing about these problems is, I cleaned my board yesterday. It's all nice and like easy to erase, right? So the thing about these semi-log and log problems is, I feel like they're easier to make sense of with numbers. He's just saying let y equal to mx plus b. So there's a difference, right, between y equal to mx plus b versus y equal to mx plus b. Right, those are two. So this one here, this is going to occur in a, I have to remember what it is. That's going to be a semi-log. And it's really, the reason it's semi-log is because half of the variables are the logarithmic variables, right? Capital Y is really log of lowercase y, and x is just x. So it's one log, one not log. Where this one here, this is log, because both x and y are the logarithmic variables. So I like to use real numbers for these, because then I'm not answering your homework questions. But really, you could take the work we're about to do here and just go back and replace the numbers I'm going to use with m and b. So your answer for this question should be something like this one. Well, in fact, let's work through this one, which is the one that is similar to 6. We'll talk about it. So let's say I had, I don't know, y equal to, let's make it interesting. He said they're positive. It doesn't really have to be positive, but that's fine. Let's say y equals 7x plus 2. And then we're going to try and rewrite this as lowercase y equal to a function of x. And the first step when you do this is to replace capital Y, or replace all your capital things with log of your lowercase things. So those are your actual variables. So we're going to have log of lowercase y, and that's log base 10, equal to log, sorry, no, that's wrong, James, equal to just what you got right, 7x plus 2. And then you're trying to isolate or solve for y, and the way you're going to get that y, well, I mean, you can think of 2 different ways. You can either say, I'm going to rewrite this equation. My base is 10 to the this power equals what's inside there. Or you can do what most normal people probably do and just say 10 to the this equals 10 to the that. And then 10 to the log of y is just y. And 10 to the that's just that. Okay, there's kind of 2 more things we're supposed to do. Because although this is correct, right, that you got y as a function of x, there's kind of a specific format they usually want you to write it in. And the format is constant times something to the x power. So I'm going to break this up. I'm going to write this as 10 to the 7x times 10 to the second. And then 10 to the 7x, I'm going to rewrite as 10 to the 7 to the x power. So this is really y equal to 10 to the 7th to the x times 10 squared, which I would write out as 100. And then, although that's fine, we usually put the 100 in front. So I would probably actually write this as y equal to 100 times 10 to the 7 to the x. If this 7 was a small enough power, I might write it out, but I don't want to write out 10 million. So if you were doing this problem with m and b instead of 7 and 2, you would have 10 to the m to the x, and over here you'd have 10 to the b power. Here we had 10 squared, so I just wrote that as 100. So that's how it would be different for the homework problem we're doing. For the other one, it's similar but different. It's still the same steps, kind of. You're going to start by replacing this with log of y equal to m times log of x plus b. And then you do the same thing you did before. 10 to the this equals 10 to the that. So 10 to the log of y equals 10 to the all of this. Oops, I was going to use different numbers. I'm going to use 7 and 2 again. Why not? They're fun numbers. So 10 to the 7 times log of x plus 2. Same kind of steps. We break this up. So first of all, this is just y. We break this up as 10 to the log of, to the 7 log of x times 10 to the second. And then before we simplify this, we can do something. We can bring this 7, in fact, I could have done it earlier. I could have brought the 7 up as the power of x. So really I've got y equal to 10 to the log of x to the 7th times 10 to the second. 10 to the log base 10 of x to the 7th is just x to the 7th, or 10 to the log of some stuff is just the stuff. So you get y equal to, I'm going to write the 10 squared first. 10 squared times x to the 7th. I would probably actually write 100 times x to the 7th, but here, since you're actually using like b is 2 and m is 7, your answer is going to probably write y equals 10 to the b times x to the m. So something to be aware of that's always true about these semi-log and log-log things is that for semi-log, if the semi-log equation is linear, the actual equation is exponential. It's something to the x power. And if your log-log equation is linear, then your original function was actually a power function, where you have something times x to a power. That's always true about these semi-log and log-log equations. All right. I bit my lip the other day. It's not feel good. So let's talk about limits. Unless there's other questions. I do have my volume on, right? Yeah. Okay. Cool. Yeah. Good. Let's see here. So I've got definitely. So I saw him talk about limits the other day in class. He was definitely talking about a lot of limits to infinity. Oh, I just minimized it. Oh, sorry, my screen went away. So he was doing a lot of limits, and so we started talking about limits as of functions as opposed to limits of sequences, which is really the same sort of thing. The only difference is that for a sequence, we only really take the limit as n goes to infinity. Whereas for a function, we can take the limit as x goes to infinity, but we can also take the limit as x goes to whatever you want. So we had been doing things like this, where we had something like, I don't know, an might have been 3n plus 1 over n squared plus 2. And we might have said, oh, what's the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of 3n plus 1 over n squared plus 2. Well, you could certainly write out some terms, right? We could say, well, a1 is 3 plus 1, which is 4 over 1 plus 2, which is 3. a2 is, I don't know, 3 times 2 is 6 plus 1 is 7 over 2 squared plus 2 is 6. But doing this is not, I mean, unless they ask you to do this, not very fruitful. All right, we're just going to keep writing out terms. That's a 10, not 101 over, is it a 10? No. Right? It's not really clear what's happening if I just keep doing this. Maybe if I plugged in some really big numbers, like if I plugged in 1,000 in my L, I get 3,001 over 1,000 squared plus 2. And that's not very big. But really, I mean, the idea isn't to plug this in. It's just to kind of have an idea of how this works. So we know that for some rational expression like this, if the degree on top is less than the degree on the bottom, this limit's going to be 0. And the way you can either just say it's 0, which I think he's probably fine with. But if you want to show a little more work, you can divide each term by the largest power of n. That's going to be the limit as n goes to infinity of 3n over n squared plus 1 over n squared over n squared over n squared plus 2 over n squared. And then you can simplify each of those terms. Notice, and this is important, I'm writing the limit in each step until I actually find it. Right? If you just wrote this instead, it wouldn't have the same meaning. Right? This is just an expression in n, whereas this says, oh, what is this expression doing as n gets really, really large? So it's important that in each step you actually write this expression, this limit as n goes to infinity, until you actually get to the value, or find that it doesn't exist. So here we get the limit as n goes to infinity of 3 over n plus 1 over n squared. N squared over n squared is 1. 2 over n squared is 2 over n squared. And then, as he definitely talked about last time, and I talked about too, anything that's divided by n like that is going to go to 0. Because if n gets really, really big, 3 divided by n gets really, really small. Same deal here. 1 over n squared goes to 0. That's just 1. 2 over n squared goes to 0. So I end up getting 0 plus 0 over 1 plus 0. Notice that now that I'm actually finding the limit, I don't write the limit expression anymore. And 0 divided by 1 is just 0. Now, you could also write this as, or it's similar to write this as if your function f of x is 3x plus 1 over x squared plus 2. You could say, what's the limit as x goes to infinity of f of x? That's just the limit as x goes to infinity of 3x plus 1 over x squared plus 2. And it's the same work. The difference between these things, which is minor, is that here you're thinking of the n values as being any positive integers, right? N equals 1, 2, 3, 4, etc. Whereas here, when it's a function of x you can think of as being anything in the domain of the function. So x could be 0, 1, 2, 3, 4, but it could also be fractions, it could be irrational numbers, all kinds of stuff. So just something to be aware of there. It's not important just yet. So there are different types of functions you can take limits of as x goes to infinity. And he was doing some interesting examples in class the other day, and it kind of makes me think we should probably do something like that, because they seem like, I felt like he spent a lot of time talking about these on Friday, so I feel like they might be important. So let's do one like what he was doing. Let's do the limit as x goes to infinity of the square root of x squared plus, I don't know, 50x minus x. And actually, I should back up one step. I'm going to back into the previous board for just one moment to say one thing. This limit here, by the way, as x goes to infinity of 3x plus 1 over x squared plus 2, if you just plug in, right, if you put in infinity for x, you get what's called an indeterminate form, where the top is infinity and the bottom is also infinity. And infinity divided by infinity is indeterminate because, or it can take any value. That's what it means to be indeterminate. It means it can have any value. And an expression like this, where it's infinity over infinity, is indeterminate. It can take on any value. Another example that's different, just to kind of remind you guys, this limit as x goes to infinity of 2x squared plus 5x plus 1 over 7x squared plus 3x plus 2. This is also an infinity over infinity limit, right? The top is definitely going to infinity. The bottom is definitely going to infinity. So it's an indeterminate form. But what do you guys know that this limit is equal to?
2/7.
Yeah, exactly. Right? When the degrees are the same, the limit as x goes to infinity is just the quotient of the leading coefficients. So here is an infinity over infinity that equals 2/7. Here is infinity over infinity that equals 0. So I want to really, really stress that indeterminate forms, infinity over infinity, and other ones we'll talk about, can end up taking on any value. Any real number, and you can also get infinity, you can also get negative infinity. And I think you can also get them to not exist. So really anything can happen. This is another indeterminate form. This is what's called an infinity minus infinity indeterminate form. I've got this part here, which is definitely getting infinitely large, right? Infinity squared is infinity plus 50 times infinity is infinity. The square root of infinity is still infinity, minus infinity. And so when we have an indeterminate form like this, we have to do something. And it's really kind of hard to work with infinity minus infinity. So the idea here, and this is what you definitely did in class, is to multiply this expression by the conjugate of itself, because maybe something's going to cancel out. But you can't just multiply by the conjugate, you have to multiply by 1. So what I'm really going to do I'm going to multiply this by, I'm going to first divide it over 1. I'm going to multiply it by the conjugate of the top part, which is the square root of x squared plus 50x plus x over the same thing. I think I wrote too big because I know I have a few more steps to do here. Let's write pen and start to down. So then when we multiply by a conjugate, the whole reason for multiplying by a conjugate is so that the middle terms cancel out. So when you, I should have done this differently. So when you multiply this times this, you're going to get this thing squared. So it's just going to get x squared plus 50x minus this thing squared. And the middle terms go away, right? You get this times x, and you get this times negative x, and they're exactly opposites of each other, so they cancel out. So we end up with the limit as x goes to infinity of, so square root of this times the square root of this is just the this, which is x squared plus 50x, minus x times x is x squared, divided by that. Sorry, I meant to do it. Okay, now we're going to do some simplifying. We cancel these x squareds. And then I'm going to see that I still have an indeterminate form. I still have something going to infinity on top, something going to infinity on the bottom. I have an infinity over infinity. Now, here's what's important to recognize about this. What's the degree on top? Everybody.
One.
Yeah. Now, this next question isn't quite right, but I'm going to ask it anyway. What can we kind of think of the degree of the bottom being? Well, I see 1, because although we have an x squared, it's in a square root. So this is like having a degree 1 term, and this is also degree 1 here. This we just kind of don't pay attention to here. So I have essentially degree 1 over degree 1, so I feel like I can kind of use the whole idea of using the quotient of the leading coefficients. But to be able to really do that, I have to kind of pull out an x from the square root. So here's what we're going to do. We're going to factor out an x squared from this term here. In fact, I'm going to do it in this step so that I can save some space. So I'm going to divide x squared plus 50x by x squared. That's going to leave me with, well, x squared divided by x squared is 1. And 50x divided by x squared is 50 over x. All right. And then we're going to pull the x squared out of the square root by taking the square root. So I end up with the limit as x goes to infinity of 50x over, what's the square root of x squared?
Absolute value of x.
Thank you. Excellent. X, pun intended there, answer. Now in this case, it doesn't matter that it's the absolute value of X, because X is going to infinity. So since X is positive, the absolute value of X here is just X. But if X was going to negative infinity, it would definitely matter. And we'd have a negative X there. So then here's what we're going to do. We're going to divide the top and bottom by X, just like we did in the previous one, right? Just like we did over here, where we divided everything by n squared. Here, we're going to divide everything by the highest power of X, which is X to the first. If I do that, I might be able to fit it all on one page. 50x over X, and then I get X squared root of 1 plus 50 over X plus X over X. X's cancel, X's cancel, X's cancel. So here's what I'm left with. The limit as X goes to infinity of 50 on top over the square root of 1 plus 50 over X plus 1. And then, since X is going to infinity, 50 divided by X is going to 0. So I'm left with 50 divided by the square root of 1 plus 1, which is 50 divided by 2, which is 25. So it's kind of weird to think that infinity minus infinity is 25. But in this particular example, it is. And I just want to emphasize once again, indeterminate forms can end up having any value. I do want to show one other variation of this. So let me flip the board here. I'll do another quick example that's similar but a little bit different. So let's see what I want to do here. Yeah. What time is it? Okay, we got a little bit of time. So here's another one that's similar but different. The limit as X goes to negative infinity of the square root of, what have I got here? X squared plus 8, no, plus, yeah, let me think for 1 second, sorry. Yeah, minus. Yeah. So if you look at this, it might be hard to see it at first, but this is also an indeterminate form because where is this square root going to? Is it going to positive infinity or negative infinity? Well, if I'm plugging in negative infinity for X, getting positive infinity here, and negative 8 times negative infinity is also positive infinity. Positive, positive, still positive. So this is the square root of infinity, which is infinity. Another thing to be kind of aware of is that when you're square rooting something, the output always has to be positive. So it couldn't possibly be going to negative. Here I have negative infinity. So infinity plus negative infinity is still infinity minus infinity. So it's still an indeterminate form. The difference in this problem is exactly kind of what Genevieve pointed out in the last one, that we're going to have an absolute value of X, and here it's going to matter that X is going to minus infinity. So if we look at this, it's the same sort of work. Oh, you know what? Oh, I'm going to change it just a little bit. Yeah, sorry. It's actually, I'm not really going to change it. I'm just going to write the X plus in first, just because I want to show an extra kind of little thing you should be aware of. Sorry. I know it doesn't really seem different, but it is slightly different. So let's do it this way. I just want to point something out. So when I multiply by the conjugate, I'm going to try and write a little bit smaller this time. So the conjugate is X minus the square root of X squared minus 8X, or X minus the square root of X squared minus 8X. All right, so when we multiply this out, you get the limit. X goes to minus infinity. In the denominator, I've got X minus the square root of X squared minus 8X And in the numerator, again, the same thing happens when you multiply by conjugates together. You get the first thing squared minus the second thing squared. And now, if we're not being super careful, we're going to make a mistake. So it's the first thing squared minus all of the second thing squared. So you definitely, if you have more than one term in your second thing, you need parentheses around that. So we're going to end up getting the limit as x goes to minus infinity. X squared minus x squared cancels, and then minus 8x is positive 8x. By the way, I should point out, we would have gotten the same thing if we'd done it the original way. If you had done, right, square root of x squared minus 8x, ooh. No, you wouldn't actually, that's fine. That's fine, you don't, and you're not supposed to. I lied. Don't look over there. Okay. So then I'm going to do the same thing I did last time. I'm going to factor out the x squared from inside the square root. So I'm going to have x minus the square root of factoring out the x squared. I'm left with a 1 minus 8x divided by x squared is 8 over x. All right, so check this out. Now the limit as x goes to minus infinity of 8x over x minus square root of x squared, just like last time, is the absolute value of x times the square root of 1 minus 8 over x. But now, here's the thing. Since x is going to negative infinity, the absolute value of x is actually negative x. Because x is a negative value, and to take the absolute value of a negative number, you make it the negative of the negative. So this is actually 8x over x plus x times the square root of 1 minus 8 over x, which is kind of funky. But really, all the works are exactly the same as the previous problem, except for this one difference, where since you're going to minus infinity, the absolute value of x turns into negative x. Whereas in the previous problem, the absolute value of, where'd you go? The absolute value of x was just x, right? So that's what we had there, and it was just x. All right, so that's the difference here. There you had x, the absolute value. Here you have negative x. And then you divide everything by x, so you get the limit as x goes to infinity. Negative infinity. Woo. Of 8x over x. So I'm just going to simplify. 8x over x is 8. X over x is 1. Minus x over x is plus 1 times the square root of 1 minus 8 over x. Just a reminder here, right? When you're dividing this whole term by x, you don't divide each factor by x. You just divide one of the factors by x. And I divide negative x by x to get just negative 1. And then finally, this thing that's divided by x is going to go to 0. So I'm left with 8 over 1 plus 1, which is 4. So that's how you do these kind of problems. They're a little bit weird. I wouldn't stress too much about them. They don't come up like a ton, but they do come up occasionally. Glass of water. Okay. Other limits to infinity. There's a couple I can think of that I think we should be aware of. Exponential functions. So things like 2 to the x, 3 to the x, 1/3 to the x, e to the x. Yeah, we should talk about a negative example as well. Okay. So, if your base is bigger than 1, like this example, and this example, the limit as x goes to infinity of 2 to the x, well, I know what the graph of that looks like. The graph of 2 to the x is your usual exponential. it does that. And if x is going out to infinity, the y values or the function values are also going up to infinity. On the other hand, now let's use red. If x is going to negative infinity, well, if x is going out this way to negative infinity, what's happening to the y values of the function? What are they seeming to get closer and closer to?
0.
What?
0.
Yeah, exactly, 0. And this is true for most exponential functions. One side goes up to some sort of infinity, the other side goes to 0. So this would be true for 2 to the x, for 3 to the x, or e to the x. Right? All of those where if your base is greater than 1, then the limit as x goes to infinity of b to the x equals infinity. The limit as x goes to negative infinity of b to the x is 0. And the opposite sort of thing is true if your base is between 0 and 1. If we say take the limit as x goes to infinity of 1/3 to the x, well then, as x gets larger and larger, you're multiplying 1/3 times 1/3 times 1/3 times 1/3 more and more times, which is going to make it smaller and smaller and smaller, which is going to go to 0. Or you can think of the graph. Exponential functions where the base is between 0 and 1 are flipped from the regular ones, and they look like this. So as the x values get really, really large, the y values get really small, close to 0. On the other side of things, if x goes to negative infinity for some exponential function with a base between 0 and 1, you end up getting infinity. Because again, if we go out this way, the y values get really, really large. Negative bases don't make as much sense when you talk about graphing. Like we would never graph negative 3 to the x or negative 1/2 to the x. They do make sense as sequences. So I just want to look at those for 1 second because I think you did talk about this and it's mildly important. And then we'll talk about a couple more examples and then we'll kind of move on to the next thing, which is limits that are not to infinity, because there's definitely a lot of limits that are not to infinity. So what about the limit as x goes to infinity? Let's use, sure, fine, of negative 1/3 to the x. Or if you prefer, the limit as n goes to infinity of the sequence negative 1/3 to the n. All right, that's your sequence a sub n. So for negative 1/3 to the n, you can see what the terms are, right? Negative 1/3, and the negative 1/3 squared is positive 1/9, and negative 1/27, and then positive 1/81, and so on. And even though the numbers are oscillating or alternating, I should say, back and forth between negative and positive, they're still getting closer and closer to 0 on either side. If I can see other people. Sorry. Yeah, those other folks. Cool. Thanks for the pictures, people. I like the pictures. Everybody else should put up pictures too. There was something here. So if your base here, or if your sequence is some small number that's between -1 and 1 raised to the nth power, it's going to converge to 0. So this is more generally true. The limit as n goes to infinity of r to the n is equal to 0 if your r value is between -1 and 1. The reason I use the letter r there is because it stands for ratio, which has to do with being a geometric sequence. But I don't think he's talked about that quite yet. And this would also be 0 for the same reason. On the other side of things, if you had a geometric sequence where your ratio was something like -4, well, then your terms would be, right, -4 to the 1 is -4, and -4 squared is 16, -4 to the third is -64, and then positive something big, 200, I don't know. I kind of have 256, and then negative something big, and then positive, right? So it's getting bigger and bigger, but it's oscillating positive, negative, positive, negative. So the thing here is, since it's not getting just infinitely positively large, we wouldn't say the limit was infinity. Here we'd have to say the limit does not exist, because it's going back and forth between positively infinitely large and negatively infinitely large. All right. Yeah. So limits cannot exist by being infinitely large, right? And although we say they're infinity, we know in our hearts they still technically don't exist. Right? They're not getting close to some regular real number. But they can also not exist by oscillating like the previous example, or like this. I'm going to do the limit as x goes to infinity of, say, sine of x. We know what the graph of sine of x looks like. Looks like this. Remember, that's 2 pi, that's pi, and so on. And you can see if you let x keep going, right, x is just going to take us on this path, and we're never going to get close to one particular value. So when you hear the word limit, you should think, oh, they're asking me, does this expression get close to one particular value? And here the answer is no. As x goes further and further out, the y values don't get close to any one value. So here we say this limit does not exist, because the y values don't get close to some value. Whereas, in fact, I think you did this other example in class, and the limit as, I don't remember if you used x or n. X goes to infinity. I think he did cosine of n times, sorry. He definitely used n. Oh well. It's fine. It's fine to interchange x and n for the most part. He did this one in class where cosine of pi x, well, if x is 1, yeah, I should be using n. We use n if we want it to be integers. We use x if we want it to be any values. Here, this one was alternating between -1 and 1. Right? Cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1. So it's kind of like the peaks and the valleys of the cosine function. Like, I know this is sine, but it's still kind of like hitting here and here and here and here. And that also doesn't have a limit that exists, because you're not getting close to one and only one particular value. This limit also does not exist.
I have a question.
Yeah.
So basically with limit, it's about how it approaches the number. Like it's about continuity, kind of, right?
It is related to the concept of continuity. In fact, continuity is defined using limits. But I would say when you're asking about a limit, and that you're really saying, what is the function doing as x or n is doing whatever we're saying? So I think that's actually, so let me just point out, I could ask a question like, what's the limit as x goes to 2 of x squared minus 1? And so what this statement really says is, what is x squared minus 1 getting close to as x, that's an x, approaches positive 2? What is the function doing as x is doing this thing? So here, I can look at the function x squared minus 1. It looks like this. And there's 1, 0, and there's 2, and there's 2, 3. So even though it might seem silly, what we can say is, oh, as x gets closer and closer to the value of 2 from either side, the corresponding y values, or function values, so if x is here, the y value is here, the y values get closer and closer to 3. So I would say that the limit as x approaches 2 of x squared minus 1 is equal to 3, because the y values are getting close to 3 as the x values are getting close to 2.
Okay, so it's like getting closer to the input, like as it approaches, like.
Totally. Now, one last thing. I know we're out of time, but I want to say one more thing because this is a really key concept when it comes to limits. When you're talking about limits, it doesn't actually, for the limit to exist, it doesn't matter what the function actually is at the value. So here's a really typical example. Let's say f of x was equal to x squared minus 9 over x minus 3. And although we could simplify that, what do you guys know is not in the domain here? Yeah. Or another way you can say that is f of 3 does not exist. However, the limit as x approaches 3 totally exists. So if I want to find the limit as x approaches 3 of this function, well, I could plug in some values, but I don't really want to because we're out of time. So the idea here really is that this simplifies. This factors is x minus 3 times x plus 3 over x minus 3. Those x minus 3's cancel. And then this is equal to the limit as x approaches 3 of x plus 3. And what I want to say real quickly here is that these are the same because when you're talking about the limit as x approaches 3, we care about what's happening as x gets really, really, really close to 3, but not actually equal to 3. We don't actually care what's happening at 3. We care what's happening right around 3. And so if you look at, so you can then say, oh, if x is getting close to 3, then x plus 3 is getting close to 6. So the limit is 6. And the graph backs this up. This function here essentially looks like x plus 3, except it's not defined at 3. So, sorry, one sec, 1, 2, 3, 4, 5, 6, 3, 3, there. So here's the graph of this function. X squared minus 9 over x minus 3. Oh, by the way, just to make sure everybody got it, here is the attendance thing one more time. Make sure you fill that out. So this is our function. Look, as x is getting closer and closer to 3, the y values are getting closer and closer to 6, despite the fact that the function actually isn't defined at 3. Same thing is true on the other side. If x is getting closer to 3 from the right, the y values are getting closer and closer to 6. So here, even though f of 3 does not exist, the limit as x approaches 3 is still equal to 6. Because I'm going to stress this many times, so I'll stress it one more time today and then we'll be done. The limit doesn't care at all what's happening at 3. It cares what's happening as we get really, really close to, but not actually equal to 3. So hopefully that will help you as we progress further talking about limits. All right, I've gone way over. We should end class. I'll see you guys all on Wednesday. If you have questions, put them in the discussion. There's a quiz, all the good stuff. Talk to you guys later. Bye.